All right, so we're going to get started with our last chapter on meteorology, which is chapter 19. There is actually chapter 20 in the book, which talks more about climate. Just in the interest of time, we had to cut that chapter out. So when we get started in this chapter, we're going to be talking about a number of different topics. This is from your book. The first thing that we're going to be doing is discussion and distinguishing the different types of air masses and fronts. Then we're going to look at the conditions that lead to the formation of a thunderstorm. Finally, next we're going to describe. Pardon me for just a second. Let me move this out of my way here. The next thing that we're going to be doing is describe the difference between an ordinary thunderstorm and the different types of other thunderstorms, such as supercells. We're going to explain how to protect ourselves from storms. We're going to describe how tornadoes form, how they're classified, and how they can cause destruction. Explain the mid-latitude cyclones and how they develop and how they affect weather. We're going to describe the relationship among weather, fronts, jet streams, and within the mid-latitudes where we are. We're going to illustrate how forces acting on the atmosphere generate hurricanes. And so then finally, we're going to explain why hurricanes are so destructive. So that's kind of the gist of what we're going to be going in this chapter. So the first thing that we need to talk about is something called an air mass. Simply put, it's a mass of air. It's a uniform mass of air, and it's going to take on the characteristics in which it's formed. So if we take a look at the North Pacific, that would be maritime polar. Maritime meaning marine, water, and polar, cold. So we would call that an MP air mass. We have maritime tropical, MT air mass, a wet, warm environment. Continental tropical, these are hot and dry, maritime tropical, continental polar. And this maritime tropical not only is in the Atlantic Ocean, but it also is in the Gulf of Mexico. And so these two are really, really important here in Missouri because this is very hot, cold and dry air mixing with warm and wet air. And there's no air masses or no mountains to cause this maritime water to drop out when it meets the continental polar. So that's a little intro of why that area is going to be very, very unique. North of the continental polar is the Arctic air. And you may hear about the Arctic front or the polar vortex. That's occurring right up here where we have that polar jet stream. So when we start looking at here in any of these air masses, they're named after where they come from. Now, as you can imagine, these are some very contrasting air masses. And when you have two contrasting air masses, they're literally going to be doing battle. And with any battle, this is where the name actually comes from, where they actually meet are going to be battle fronts. And so we're going to call these fronts. And so when we start looking at fronts, if a cold air is advancing, it's called a cold front. If a warm air is advancing, it's going to be called the warm front. And these fronts move at different speeds. Cold fronts move faster than warm fronts. So if a cold front catches up to a warm front, what's going to happen? It's going to push all of that air up and it'll create an occluded front. We'll look at those in just a second. And then we have stationary fronts. This is where no air mass is advancing. And you just have two air masses right next to each other. Now, if you're not having a front and you're in the middle of one of these air masses, you're having very uniform, consistent temperatures. But when these fronts occur, these are going to bring weather changes. If you're on one side of the front and then you move to the other side of the front, you're going to have a change in wind speed, wind direction, and usually when these fronts are approaching, warm air is getting pushed up and it's going to cause some rain right in that on those fronts. So here's a cold front. If we start looking at this cold front a little bit more from a visual standpoint, you can see that this cold air is advancing. And if you were here watching this front come towards you, you'd see these very tall clouds of vertical development. So maybe some anvil heads like this one is shown here. On a map, they would actually show on on a weather map, they would actually show these little blue teeth coming off, or blue icicles, as this cold front is advancing. When this cold front is advancing, it's pushing that warm air up very quickly. And again, warm air can hold a lot more water. And so it's going, when it rains out, it's going to produce usually heavier rains. This air is getting pushed up to the top of the troposphere. And after the cold front has passed, you're in the middle of another air mass. And so if you were in warm air, the cold front comes through. Right after that, you're going to be in this cooler, drier air. Now, warm fronts also advance. If this warm air is pushing up, as this warm air is advancing, you're going to see these little half suns to show us it's a warm front. Usually these are in red. The other one, the cold fronts, are in blue. But as this warm air is advancing, it's not as strong, it's not as forceful. And so as a result, what's going to happen is it's going to get pushed up as it's advancing. And so as a result, you're going to see these moving much slower. So you usually have more lead time when we start looking at these warm fronts. Then these warm fronts are going to start off with stratus clouds, cirrus clouds, and then stratoclouds and altostratus clouds, and then finally some nimbostratus clouds as this rain is approaching. These are not really forceful, heavy downpours, but more of just a consistent, steady rain associated with these warm fronts. And again, beyond the warm front, the air would change directions, and you'd end up with clear skies. And after the rain, it would be a lot warmer, because you're going from a cold air mass to a warm air mass. So as these cold fronts are advancing and these warm air fronts are advancing, the cold air moves a lot faster than the warm front. And so as a result, what's going to happen is the cold front is actually going to catch up to the warm front. And when that takes place, it's going to create an occluded front. So this occluded front occurs where the cold front advances and it has caught up to the warm air. So right at that occluded front, you're getting this mixing of air where you may end up with clouds and rain right at that occluded front. This is going to push all of the warm air up. And to show this, it's usually in purple, or I have also seen where they will alternate a blue triangle followed by a red circle. These are all in the same direction because the air is getting pushed in from our vantage point here to the right of the screen. And these cold fronts, again, is moving faster than the warm front. So all of this air at the top is warmed up. Eventually, once all of this air rises, we're going to have a uniform air mass again, with cold air on both sides, warm air above, and that warm air is going to dissipate, and you'll end up with the front dissipating. And then the last front we have is one I usually start with, but I didn't today. It's a stationary front with warm air on one side, cold air on the other, and neither front advancing. To show this, that we have this front here, what we're going to end up with is we're going to end up with this neither air front advancing. This mixing of the cold and warm air together is going to lead us with weather on these fronts that can last a long period of time. So as I said, I usually start with this stationary front. And so what can happen is this stationary front can develop. We're going to look at this in just a second, but what can happen is a cold and a warm front can develop around a low pressure system. The cold front advances, leaving to the warm front moving slower. In this greenish color, you'll see that the rain occurs in front of a warm front, but it's usually right at the cold front. And so as that air is getting higher and higher in the sky, the clouds are getting lower and lower in the sky, excuse me. What you're going to see is that rain very slow approaching. And so when we start looking, and here we have the occluded front occurring, where the warm front has been overtaken by that cold front. And then finally, that low pressure out, we're going to have a uniform air mass, and the low pressure center dissipates. So when we start looking at severe storms, we're going to look at the first severe storm is called the thunderstorm. And I'm sure you're very familiar with these thunderstorms, consistent with towering cumulonimbus clouds, again, puffy rain clouds. And these produce tremendous amounts of lightning and thunder. Now, thunder, as you already know, is the rapid expansion of air associated with lightning. The lightning is actually causing the thunder. It's causing that air to very quickly heat up. And so thunderstorms take place frequently in some places on Earth, but rarely in others. And this makes a lot of sense that we'd have areas that have a lot of moisture in them, and warm air holds a lot more water than cold air. And so we can see that we have a lot of lightning right around the equator. When we start looking at about 30 degrees north and south latitude, that's where that air is descending, and we don't have as much lightning, oddly enough, when we have areas of deserts. Up in the northern regions here, we have very little lightning because the air is so cold, there's not much moisture in the air to begin with. And if there's not much moisture to begin with, that's a real clue that we're going to need moisture in order to create these lightning thunderstorms. So here's a map of the United States showing those thunderstorms and where we have these thunderstorms. We can see here in Missouri, we get about 50 to 65 of them a year that we have these thunderstorms. So when we start looking at where do we have the most of them? Oh, where the land is sticking out into the ocean on both sides, whether it be the Gulf of Mexico, the Atlantic Ocean, and that's in the southeast part of Florida. And so we can see there's a tremendous hot, humid environment here, creating a lot of thunderstorms. So what are the conditions needing for thunderstorm? Well, the first thing that we need is moist air in the lower portion of the atmosphere. And so if you've ever been down to the swamp of South Florida, you know that it's hot and wet in the air, the high moisture content and high temperatures. So high relative humidity. And so all it takes is just a little bit of that air to rise up, and it's going to get rid of a lot of water. From the lab that you've done, hopefully you realize that warm air holds a tremendous amount more water than cold air. And so what are some things that can cause the air to lift up? And that is an updraft. And so we can have some uneven heating of the earth that can cause this updraft. We can cause a cold front to push this warm air up. And so something that's going to push that air up very quickly. And then finally, atmospheric instability. And so we'll talk about this instability here in just a second. So when we start looking at frontal lifting, again, this is when a cold front is advancing. It's going to push that warm air up. And if that air gets pushed up very quickly, what's going to happen is it's going to give off water and heat. Remember that when water is condensing out, it's getting rid of that latent heat. Well, that energy has to go somewhere, so it's going into the atmosphere. As a result, it's causing that air around it to be warmer, and so it's going to cause that air to rise up more. We call this unstable conditions. And so as a result, that air is going to rise up all the way up to the top of the atmosphere. And this is what we call building clouds. And you can see that that updraft will actually cause that air to have some inertia. It'll actually go above the top of the troposphere. And so we can see it popping up at the top of this troposphere. You'll see that these clouds at the top of the screen here are all relatively flat, because above this, the air is warmer. And if the air is warmer than the air above is warmer, that air is not want to rise up any longer. And so that is true for most of the case, except for right where the air has that updraft. And where it has that updraft, it's got that inertia. And so it will slow down very quickly. creating that little bulge there that you see there. Now, when this air is rising up, what's going to happen is it's going to cause these very strong rains clouds. And so we can see that front advancing right at the edge of that cold front advancing. We can see heavy rains getting pushed up. And so if I said, if I looked at this, the winds would be out of the northwest in this region. And very quickly, you'd see Mac getting drenched with rain. But after this, after the front has passed, the cool air would be behind here. You'd have some dissipating, maybe a few fair weather clouds right after that cold front passes. And so this is a fairly common occurrence. So if we have two cold front, yeah. And so the second type of thunderstorm is not associated with a cold front per se. Much more, it's associated with two dissipating storms. And so if we have two older storms, what's going to happen is it's going to push that air together. And so right at that area, some of this air is going to get pushed up. And if we have two air masses pushed up, what's going to happen is you're going to create a new storm with this buoyant air around here. And again, when we have the air rising, it's going to cause that water to and heat to be let out. When this heat is let out, what's going to happen? It's going to heat the air around. It's going to cause more of an updraft, and it's going to cause that air to become more buoyant. And so, if we go back to the cold front, in this area where the clouds are dissipating, if we're pushing all this air up, what's going to happen is that right in the back area, after the storm dissipates, it's going to create a downdraft. So we have got an updraft here and a downdraft over here. And so here is that downdraft from this slide. And so if two air masses are coming together, what can happen is it can actually cause what's called a gust front. So which of the following lifting mechanisms is closely associated with downdrafts associated by nearby thunderstorms? Oh, if we go back one slide, oh, this is this gust front. Now, I mentioned instability. So I want to refer back to a previous slide, and I just zoomed in on that troposphere. And as I've already mentioned, in the troposphere, the higher you go, the colder it gets. And we can look at this rate, and it's very, very consistent here. We call this the environmental lapse rate, the rate at which temperatures cool with elevation. And it's a very consistent line here, where the higher you go, the cooler it gets. The higher you go, the cooler it gets. And so this is known as the environmental lapse rate. And this is associated with the air striking the earth right at the earth's surface, heating up that air. That air will rise and cause, the further you are away from the air, the further you are away from the Earth's surface, to cause it to become a little bit cooler. So that's what's happening here in the troposphere. Now, this is known as the environmental lapse rate, the rate at which the temperature decreases with altitude, and it's known as the environmental lapse rate. Now, if we have condensation occurring, you're adding heat, you're changing the rate. And so in some cases, you can actually cause updrafts associated with latent heat. So if we see this, all right, so when we start looking at air, remember that when water is condensing, it's giving off this latent heat. And so on a hot summer day, we might end up with conditions very similar to this, either on the slope of a mountain, or whenever we have two different conditions causing some differential heating. So what's going to happen in this case is what we're going to end up with is warm air rising, and if that warm air is rising, it's going to give off water, and when it's giving off this water, it's giving off heat. And so that heat is going to cause that air to become more buoyant, and it's going to cause that air to rise up till we get to the top of the troposphere. Now, these conditions, this is what we call conditionally unstable air. Now, we just got done talking about the lapse rate, the temperature at which air cools as it rises in the atmosphere. So if we start looking in the troposphere, the higher you go, the colder it gets. And that's that black line here. And when we start looking at stable conditions, maybe we're in the middle of a high pressure system. If air is starting to rise up, we're looking at in the blue line is this dry air that we don't have to worry about condensation occurring. So if we start looking at that blue line, it's always going to be, that air is always going to be cooler than the air around it. And so as a result, if the air rises, it's going to cool off. We call this cooling associated with the air, change in air pressure is called adiabatic temperature change. And so when we start looking at adiabatic temperature change, this is just association with the air expanding, it's going to cool off. We can actually, last lab, excuse me, 2 chapters ago, we looked at this. When I squeezed the air in my 2-liter bottle, I could actually increase the temperature of that and cause the water vapor to go into a liquid state. When I release that pressure, I cause the air to expand and the temperature dropped. We do this all the time with things like air heating and cooling. When we look at an air conditioner or a refrigerant, what we're doing is we're expanding that air, using a vacuum to expand that air. When air expands, it cools, and as it cools, if the air compresses, it's going to heat up. And so we have this air. Anytime the air is rising up, it's going to have less air pressure around it, and as a response, it's going to cool off. And that's adiabatic temperature change, adiabatic expansion. So when we start looking at this blue line, this is when air is forced up, and we don't have to worry about that adiabatic temperature change. But if we have moist air is going to have water in there. And if we have this water, if we cool the air down, so not only is the air going to cool off because of the decrease in pressure, but we're also getting that phase change. And when you're adding water into the environment, taking it out of the air, you're adding this excess heat. And so this gap in between here is this is that latent heat, that heat associated with air, the heat associated with the phase change from liquid, gaseous air, water to liquid water. And so as a response, if we have stable conditions, both the moist air and dry air, when it rises, it's always going to be cooler than the environmental lapse rate. And so that tendency of that air is going to want to sink back down. But if we look at the right here, we have this conditionally unstable air. If the air doesn't have any condensation occurring, it's going to always want to sink back down. It's cooler than the air around it. But if we have moist air and we start causing that condensation to occur, what's going to happen is going to add that extra heat to that upper part of the atmosphere, which in turn is going to make the air less stable. The air is going to be warmer. It's going to have a tendency to want to rise back up. Your book gives the example as a take. We can do this as a mental exercise, a mental experiment. If you had oil and water, and so oil is less dense than water, and so as a response, it's always going to want to rise back up. Now, if I took a spoon and I pushed that oil back down, what's going to happen is when I release that spoon, it's going to want to rise back up. When we start looking at air, this conditionally unstable air, this warm, moist air has a tendency to rise up, and it will rise up to the top of the troposphere if you start getting rid of some excess amounts of water. You're giving off that extra heat. You're making it warmer than the air around it. If it's warmer than the air around it, it's going to have a tendency to rise up. If it's rising up, it's going to give off more water. If it's giving off more water, it's going to give off more heat. It's going to be less buoyant. And so it's going to want to rise up even more. And so if we get air starting to rise up, what's going to happen is it's going to build through the rest of the afternoon and usually be followed by those afternoon thunderstorms you may be familiar with in Missouri summers. And so we call this atmospheric instability, unstable air. Air wanting to have a tendency to, once we get it going, it's going to want to continue to keep going till it gets to the top of the troposphere. And these are what we call ordinary thunderstorms, usually around here in late afternoon after we heated up the day, pockets of air for the entire day. Maybe we have a blacktop surface, and so as a result, it's going to take in more heat, so it's going to give off more, take in more sunlight, so it's going to give off more heat, and as a response, it's going to become very, very, very unstable. So what starts to happen if we start looking at this slide during a normal, ordinary thunderstorm, we have the development stage here, where let me move this guy around here. An ordinary thunderstorm. What's going to happen is warm, moist air is lifted up, and again, this happens. Air can get pushed up over a mountain. Air can get pushed up because because we have a little area that is warmer than the air around it, so it's going to want to be rising up. And so during the building stage, what's going to happen is the air is going to rise up, and as the air is rising up, what's going to happen? It's going to create an updraft. And if we are dealing with a updraft, what's going to happen is that air is going to rise up right here in this thunderstorm, and this updraft is going to be cause a current here. Now we can end up with this condensation occurring. It's going to start off as little droplets of water, and then if the air is continuing, those droplets of water are going to get more water accumulating. They're going to be the condensation nuclei, and those what's going to happen is little bits of ice called grapple are going to build on these. Eventually, what's going to happen is those bits of grapple or bits of small ice are going to, let me get my arrows here. This little bit of droplets are going to start to fall back down to creating a downdraft. And the updrafts and the downdrafts will eventually cancel each other out, and we'll end up with a dissipating thunderstorm at the end of this with a gust front. So if we start looking at these are very, very common to see these anvil head clouds, these clouds of vertical development. The reason why is, again, once we hit the top of the troposphere, above it is the stratosphere, where the air is warmer the higher you go, and so therefore the air is really, really stable up in this area. The higher you go, the warmer it gets. Air wants to be the right buoyancy, and so as a result, if the cloud has enough of an updraft, it does overshoot a little bit, it'll actually dissipate back down to create these anvil heads. What do we call one of these clouds? An anvil head cloud. So whenever we have a series of isolated thunderstorms like this, what can happen is they can start to merge as a result of that gust front, and we're going to end up with these angled storms here. This is where they're starting to build, and then they can actually start to accumulate, create this heavy line of precipitation associated with that gust front. With that gust front, it's pushing all that warm air up, and so right along this gust front here, you end up with those heavy bits of precipitation. And in some cases, you end up with a frontal squall line. This is associated with a cold front advancing. When the cold front is advancing, you'll notice right at the beginning of this area, the air is getting pushed up really, really quickly, and this is called a squall line. So a squall line is a sudden, sharp increase in wind speed lasting for a few minutes, where the gust fronts are lasting only a few seconds. When we start looking at these, again, these squall lines, the word squall comes from it's more like a brawl and a squeak, and so that's what's happening right along that area, where you end up with this massive, heavy, strong winds all in the same direction. When again, these are usually associated with cold fronts in a mid-latitude cyclone. We'll talk more about mid-latitude cyclones here in just a second. And then finally, we have supercell storms, and these are very long-lasting, rotating updrafts. So as we start looking at these supercells, well, let's look at them a little bit more in depth here. A thunderstorm containing a particularly large, long-lasting, rotating updraft is called a supercell. And so when we start looking at supercell developments, we have to remember back in our last chapter on winds, we said that winds near the Earth's surface have friction associated with them. The air in the upper part of the troposphere has what geostrophic winds that are moving much faster. And what can happen as a result is, if you look at this image from your book on figure 19.8, the air is starting to roll around at the top of the troposphere again, because that upper air is moving faster than the air at the Earth's surface. Additionally, what can happen is you'll notice that the high air winds are moving at a different direction than the surface winds. This is creating what's called wind shear, when winds are moving in two different directions. And then if we had some uneven heating of the Earth in this location right in the middle of this slide, what's going to happen is that air is going to start to rise up. If that air starts to rise up, what's going to happen in these supercells is the air will start to condense. Again, air trying to fill in that low pressure in the center. Due to the Coriolis effect, these are going to be in counterclockwise fashions. And as a result, what's going to happen is these supercells are going to want to, again, air filling in this region, creating this very strong updraft. So these can lead to some even more severe storms called hurricanes. So we also have mesocyclones. Again, mesocyclones are counterclockwise rotating updrafts of supercell storms. And so when we start seeing these mesocyclones, or middle-sized cyclones, these can create some very strong storms. Particularly, these can actually trigger some tornadoes. We're going to talk about tornadoes here in just a second, but before we do, we need to talk about something else associated with severe storms or dangers in the air, and that's lightning. Lightning is caused from the electrostatic discharge when negatively and positively charged atoms, positive charged atoms are called ions, become separated from the clouds of a thunderstorm. And it doesn't have to be clouds. This static charge is the exact same thing. Anytime this was first discovered when people took a piece of amber and a piece of fur and they rubbed them together. And what you're doing is you're transferring ions, extra electrons from one object to another. And when they're allowed to build, they can try to discharge. And this is lightning. This is electricity. And so electrons can be from cloud to cloud, or from cloud to the ground. as a response to this discharge of these excess amounts of electrons. So lightning discharges in in three ways: negatively polarized charges. So again, negative polarized, it means they have an abundance of electrons. So abundance of electrons go from the cloud to the ground. And so that's cloud to ground lightning. And you can actually see that in this case. Positively polarity clouds to ground strikes. So if you had excess amount of electrons in the ground and not enough in the cloud, what you're going to end up with is the lightning go the other way. And then cloud to cloud lightning strikes. So whenever any of these occur, what's going to happen is the air is going to heat up very quickly. Energy passing, this electricity passing through the air is going to heat up that air. And when that air heats up, it creates a sonic boom, and that sonic boom is registered as thunder. And so that's really why we have thunder, is because the air heats up very, very quickly, a rapid expansion of air. And so it doesn't matter if it's cloud to cloud, cloud to ground, or ground to cloud, all of which is going to produce thunder. So cloud to ground lightning here was going to occur whenever you have an excess amount of electrons in this cloud. And again, water is a universal solvent. I think I've mentioned this probably about 6 times by now, which means it has a positive side and negative side. And so if you start brushing up this water movement in the same direction, you can start to build up an excess amount of electrons. Just in the same way that if I took a piece of carpet and my shoes, I can start to build up some electrons. And depending on whether I'm building up electrons or getting rid of electrons, it really doesn't matter. We just have the unbalance of electrons. And so if the area that has the extra amount of electrons or negatively charged particles, what's going to happen is the electrons are going to want to return, are going to want to discharge. And so if we can somehow, unfortunately, this was really, really dangerous. It's going to find the path of least resistance. And so if we had a area that had an extra amount of electrons right at the surface here, maybe this water from the tree, this would, I would be surprised if I were drawing this, I would show those electrons going, or the lightning hitting this tree. Maybe it is. So it's striking this tree. And so it's creating this series of electron return, just dissipating this, those extra amounts of electrons. Now, this caused all sorts of problems. It burned down houses because, again, this rapid heating of this liquid here, it caused trees to rapidly expand and splinter apart. But we realized this, and we realized that these electrons, we now know they're not fluid as we once thought, but in fact, subatomic particles. But we now know that if we can create a positive stream on the ground, what we can end up doing is putting up a piece of metal. Metal is a really good conductor of electricity. And so as a response, it can actually cause the electrons to dissipate into the ground and not hit a tall building or a tree and causing the damage. So as a response, we can actually direct where this lightning is going to be striking. And so as a response, we here at Mineral Area College have actually put up lightning rods to direct the lightning away from our sensitive servers and internet and power lines and to the lightning rods around the college. And so if you look around the edge of the college, we can actually see these lightning rods. And so when we start looking at what type of lightning is associated with stepped leaders and positive streamers associated with cloud to ground lightning. Incidentally, if you're on the ground and you start having your hair rise up like a Van de Graaff machine, like at the Science Center or the Magic House, where you touch this machine. And what this machine is doing is the exact same thing that you're experiencing here. It's causing a charge in excess amounts of electrons or lack of electrons. And anytime you have all of those extra electrons, remember that opposites attract like repel. And so if you have a bunch of extra electrons, what's going to happen is your hair is going to stand up, because each one of those particulates on your hair have those bunch of electrons, and they're going to repel one another. And that's what happens, is causing your hair to rise up. Same thing if we were removing those electrons. But then what they will end up doing is discharging this electrons, and you'll see the big spark occurring with that Van de Graaff machine. The extreme release of energy can cause trees to explode, ignite flammable material, blow out electrical transformers, permanently harm and instantly kill a person or animal that kills it, because again, that rapid expansion of heat from the electricity passing through can mess up your electrical system, including your heart. And so there's all kinds of problems. So don't get struck by lightning is what I'm saying here. And so when we start looking at the lightning, it's associated, again, it's the exact same scenario as static electricity. It's just a lot larger. When we start looking at microbursts, or excuse me, downbursts, are very strong outrushing of strong downward moving air. And so when the air is moving down, it's going to hit the ground and can't go further down anymore. And so as a response, it's going to be going in all directions away from a dissipating thunderstorm. And so this can be somewhere between 30 and 100 kilometers an hour, so about 60 miles an hour tops. But it's going to create these straight line winds. In the summer of 2020, in late August, there was some straight line winds. The technical name is derecho, where these straight line winds are going to cause huge problems with farming in in Iowa. These straight line winds caused massive trees going down, as well as crop damage. So these straight line winds can be caused from downbursts or microbursts. Now, when you start looking at the updrafts are going to cause particulates of water to get blown up. And so gravity is going to cause those particles of those grapple bits of water or ice to fall back down. And so this air moving up and down, up and down, up and down, what's going to happen is those ice particles are going to get bigger and bigger and bigger. And then one of two things are going to happen. Eventually, what's going to happen is the downdraft is going to end, causing the hail to form, or the downdraft is not going to be strong enough to keep these large particles in the air, and the hail is going to fall. And so these are very, very discrete areas that have hail, but they're obviously hail is, we can see here, can be quite large. Those look like about centimeters there. So this looks to be a hail, let's see, 9 centimeters, so about 4 or 5 inches across. Hail is also commonly referred to by different spherical objects like golf ball or baseball or softball, which we had a couple of years ago at the college. So when we have a cold front or a rapid movement of air, so as the air is getting pushed up, this can create the hail in this updraft portion. And the hail can actually go back up and down, up and down, up and down. And then finally, when the hail, or when the front passes, that hail can come back down and fall as very discrete layers. So these severe storms can, in fact, trigger things like tornadoes. So when we start looking at tornadoes, there's some tornadoes that that occur over water. These are known as water spouts. And here we can see one of these water spouts here and here. So when we start looking at these tornadoes, not all of them are these peaceful little small tornadoes or water spouts, but they can be violently rotating funnels or vortices of air that extend from the ground up to the base of a severe thunderstorm. So in order for it to be a tornado, it needs to actually have touched down. Otherwise, it would just be called the funnel cloud. So when we start looking at these tornadoes, we can actually track them. And there's definitely a pattern to these tornado tracks. They're all moving from the southwest to the northeast. And so these paths here are, we can see these are tracks that are looking south of, just south of us here. And you can see they're all moving in the same general direction. So when we start looking at formation of a tornado, a lot of these are going to be occurring in mesocyclones or middle-sized cyclones associated, again, with rapid infilling of a low-pressure center associated with upper air moving faster and in a different direction than the lower air. And so this is going to create some very unstable air. That air is going to start to rotate, move like this, where the upper air is moving faster than the lower air, and then that shear is going to cause that air to kink or rotate, turn. And so as a result, what we're going to end up with is the air moving in the same general direction from the southwest to the northeast along these tracks. So we've already looked at this earlier, where the air started to kink up there, and in these mesocyclones, what we're ending up with are these tornadoes moving from southwest to northeast. So if we start looking at where we'd expect to find these tornadoes, they'd be right in the southeast portion of the mesocyclone. And so when we start looking at this mesocyclone, what's going to happen in the rear flank of the downdraft, the air is going to start to roll over and move down at the same time that the air over here is, in this case, is moving to the right from our vantage point. And so this air rolling over here is going to want to fill in. And so what's going to happen as that air starts to fill in, it's going to start spinning faster and faster. Just like an ice skater, when they will pull their arms in and spin around, they're going to spin faster as they're getting a tighter circle. And so as a result, that's going to cause these tornadoes to occur. Now, tornadoes are named, Dr. Fujita originally looked at the damage associated with a tornado, and then he deduced exactly how fast the winds were moving, looking at objects that were shoved through different materials. With the advancements of high-speed film, high-speed photography, as well as these days we can use radar to figure out how fast the winds are moving. And so we had to modify his original scale. So it used to be the Fujita scale, excuse me. And so now it's the EF, or the enhanced Fujita. It's been modified ever so slightly to accommodate this scale. And so this goes from an EF0 to an EF5, and there is no EF6. Again, 6 is the fastest that you can get, because it is anything with wind speeds over 200 miles an hour. So when we start looking at categorizing wind speeds of tornado, it is the EF scale, the enhanced Fujita scale. These are only looking at the speed at which the wind is moving. But we can see that the faster the wind is moving, the more damage it's going to do. And so we can look at the damage from a tornado and the path in which it's touching down. And so when we start looking at where we have tornadoes, by and large, this area here is known as Tornado Alley, areas that are really rich in tornadoes. The reason for this is we've got the Rocky Mountains to the west, the Appalachian Mountains to the east. And in between these Great Plains, we've got back to the beginning of this chapter, we've got maritime tropical air right here and continental polar air right here. We also looked at where the intense rays of the sun are, and in the spring, what's going to happen is every single day, the intense portion of sun is getting, most intense part of the sun is getting further and further north. So it's bringing up that warm, moist air at the same time that we still have cold air to the north. And so this very, very strong contrast between maritime tropical air and continental polar air mixed with air coming down off of the Rockies, moving very, very fast at upper air portions. And so as a result, the combination of those three things is going to make us here in the United States the biggest or the most intense areas for tornadoes as anywhere else on the earth. If we take a look at other latitudes, other areas that have those same latitudes, where we have our spring, where the sun is getting higher and higher, closer to the North Pole in the northern hemisphere and closer to the South Pole in the southern hemisphere in their spring. All the other mountain ranges, if we take a look at like the Alps or the Himalayan mountains, those are east-west trending mountain ranges. And so anytime air gets pushed up over the mountains, it's going to drop all the moisture out on one side of the on one side of the mountain. And so we're going to end up with some heavy rains on those back sides of the mountains. And so here we don't have any mixing of those, anything impeding those two air masses from mixing. And so as a result, we have tremendous amounts of tornadoes in this area known as Tornado Alley. So the last thing when we start looking at, or one of the last things that we're going to start looking at, is something called mid-latitude cyclones. Now, a mid-latitude cyclone occurs, actually is driving a lot of the different weather patterns that we have here in Missouri. These are cyclones. So by definition, a cyclone is a low pressure center. The opposite of a cyclone would be a high pressure center. Now, when we started looking at this in previous chapters, we didn't really call them cyclones and anticyclones. We call them low pressure and high pressure systems. A low pressure center is going to cause air to rush towards the center, and due to the Coriolis effect, it's going to move in that counterclockwise fashion. High pressure centers are going to move away from the center and moving in a clockwise fashion. And so it's going to diverge in the center. And so if we start looking at convergence of air and divergence of air at the Earth's surface, the exact opposite is going to be occurring at high altitude. So if air is coming together at elevation at the top of the troposphere, what's going to happen is that air is going to come down and push away from the center at the Earth's surface, and we'd be at high pressure. If air is sinking, air is going to warm up and it's going to get squeezed together, causing it to warm up, and as a result, it's going to hold more moisture, and so the humidity is actually going to go down, or how much water the air can hold. And so as a response, high pressure centers are going to be associated with clear skies. The exact opposite is happening with these low pressure centers. In a low pressure center, the air is rushing towards the center of that low pressure, filling in that air, causing some of that air to rise. Well, we know that when air rises, it cools. It can't hold as much water. And so this is going to be associated with cloudy skies. And so if we start looking at air moving counterclockwise flow of air in the northern hemisphere creates a divergence at the center, at the base, at the bottom, is going to be a high pressure center. And on a weather map, these would be H's and L's. So the reason why we end up with these mid-latitude cyclones is going to be associated with the difference between the two different types of air that we have, and two different types of winds that we have here in the United States. Now, by and large, we are going to be impacted by the westerlies here in Missouri. The air is moving from the west to the east. And to the north of us, we have the easterlies, the air moving from the east to the west. And again, this is due to the Coriolis effect and the Hadley cells that we talked about in previous chapters. And so as a result, what's going to happen is the air is initially blowing on this frontal boundary, and so in this case, we would have started with the stationary front with this cold air starting to advance on this left portion, and in this case, the warm air is advancing, and it doesn't matter which one is going to dominate, but either case is going to cause this air to start moving in a counterclockwise fashion. And as this counterclockwise fashion is occurring, it's going to push that warm air up, and it's going to create a low pressure center right in here, right in the middle where those two air movements are circulating. And again, we can think of this as if we had two opposing rivers moving in opposite directions. The westerlies in one side, the easterlies in the other side. And so every once in a while, they're going to catch and create these eddies. These eddies would be the low pressure center. And so eventually what's going to happen is the cold front is going to reach the warm front, and we'd have an occluded front right in that area. And then finally, the last step in this is that the low pressure center would, all the air would fill in that area. We'd have a dissipating pressure system. Now, these mid-latitude cyclones are crucially important for weather around here. Again, these eddy currents. Cold air moves faster than warm air. And so as a response, these cold fronts can be causing some severe storms, especially in the wintertime. We have blizzards associated with these. These can create tornadoes and strong thunderstorms, particularly along the cold front portion of this cyclone. And so here's an idealized situation here of a classic comma shape associated with a low pressure center. We can see that if we were right here out front of the cold front, the warm air would be coming from the south, and then after the front passes, the air is cleared out and moving from the west and northwest, and so we have a distinct change in weather in the direction of the weather. We can see in this case, if you had the warm front, the air would be moving from the southeast up into this region. And so this air is moving basically in this hook shape, creating these clouds associated with the air rising. So mid-latitudes can cause thunderstorms, yes. Blizzards, yes. Ice storms, yeah, it's again, air rising up. The term nor'easter, we don't really deal with too much here in Missouri, but off the coast of the eastern seaboard, we end up with air moving these winds here, very violent portion of the storm from the northeast coming down, particularly these heavy rain or heavy snows coming down. These are called nor'easters. And so that's named after where the winds are coming from the northeast. So yeah, it can create nor'easters. So it would be all of the above. Now, when we start looking at weather patterns, these mid-latitude cyclones are many times directed by what's happening up in the northern portion, or what's happening up in the upper air, and that's the jet stream. And so if we have a hook in the jet stream, it can actually deflect and move these mid-latitude cyclones across the United States. We call these trains, where we have a mid-latitude cyclone passing over a mid-latitude cyclone over a mid-latitude cyclone. We can also have these in the southern jet stream, where we end up with the same conditions, creating those eddy currents following that same path. And so we have three different, in this case, areas that are potential for hurricanes, all in the same path. And these are called trains. Now, in any of these cases, what we're really trying to do here is redistribute this heat that's because the heat on Earth is unevenly heated. The sunlight is hitting at different angles. It's hitting water. Some of that heat is dissipating more than if we hit a darker surface. And so the ultimate goal of why we have these weather patterns is we're trying to balance out the heat in these systems. And so when we start looking at this mid-latitude cyclone, it's a complicated series of conveyor belts that are just trying to move airs from high pressure to low pressure um, as it continues to evolve. And just like if I were to take a balloon and fill it up with air, I let the balloon go, that air is wanting to go from the air inside is at a higher pressure than the air outside. And so it will try to balance itself out. When we start looking at another classic severe storm, and this is called a tropical cyclone. Now, here in Missouri, or here in the United States, actually, we refer to these typically as hurricanes. That means a very specific thing. That means it's going to be hitting the United States or North America, usually out of the Atlantic Ocean from, but if we were in hitting out of the Pacific Ocean, hitting Eurasia, we call these typhoons. If we were in the Southern Hemisphere in the Indian Ocean, we'd call them a cyclone. So all of which are the exact same thing. They're all using the exact same scale that uses wind speed, which is the Saffir-Simpson scale that's going to be, again, based on the sustained wind speed. Now, 2020 has been a real strong year of these number of hurricanes. When we start looking at conditions like this, we can see these different developments, and they're all going to be starting right here. We have the uneven heating between land and water. And so as a result, this uneven heating is going to create a series of thunderstorms. And this these thunderstorms can combine to create large, severe low pressure storms called hurricanes. And looking at the lowest pressure difference, again, wind pressure pressure gradient is going to cause us to have the air moving. And so tornadoes are going to be faster moving winds, so they would have a lower pressure or a steeper pressure gradient. But these are going to be very large areas. When we start looking at these large areas of hurricanes, these are driven from the latent heat of the ocean. So if we had really warm water in the ocean, what's going to happen is that warm water, get my arrow back here, my warm water and air moving over the ocean is going to cause that latent heat to cause evaporation. As the air is going to rise up, what's going to happen is it's going to give off more of that latent heat, and it's going to in turn cause more heat in the atmosphere. This latent heat in the atmosphere is going to cause more of these winds to move. And so if this continues, the hurricane will build and build and build. It'll create its own separate rain bands now in the middle of this hurricane or typhoon, what's going to happen is the air is actually going to fill in this region. And so right in the middle of this hurricane is the eye, where the air is sinking. Air is sinking, warms. And so if the air is warmer and sinking, what's going to happen is the cloud, you're actually going to have a clear skies right in the middle of this eye. Now, you can actually fly over these hurricanes if you stay up in the troposphere. And so we do this often. We'll fly over the hurricane and take some readings, measure what's going on to help us try to better track these hurricanes. So these individual rain bands associated with the air moving in this spiral fashion. So the reason conditions that are going to be favorable, again, the energy source for these hurricanes are the warm tropical waters. Now the rotation associated with these are going to be associated with the Coriolis effect, which deflects to the right in the northern hemisphere, to the west and to the left in the southern hemisphere, which means that if you're right on the equator, the hurricane doesn't know which way to go, and so it will never form. And so as a response, what's going to happen is these hurricanes are going to follow this exact same this path. So again, warm water, a cluster of thunderstorms, usually associated off the coast of Africa because the air is going to heat up more on land than it is in water, and so you get this differential heating, and so you're starting to get these thunderstorms starting to build up. The trade winds are going to carry these this set of thunderstorms and start to amass these thunderstorms. What's going to happen is going to develop a tropical storm, and if we had enough, if conditions are favorable, meaning we have warm enough water, we don't have some upper movement of winds that can dissipate this, or if it moves over land, it'll stop the evaporation, and we don't want that one occurring because that means that the hurricane has made landfall. And so any one of those three things can happen. If the hurricane moves up into colder waters, it's going to dissipate because it won't have enough evaporation, enough energy to cause that hurricane to fade. So if we start looking at the path of hurricanes here, cyclone, typhoons, we can see that they always are moving in the northern hemisphere. They're forming off, following those trade winds, and then they get caught into the westerlies, get caught in the trade winds, and then up to the westerlies. And so this Coriolis effect. If we take a look at the southern hemisphere, it's just the opposite. And as it turns out, the Coriolis effect is actually going to cause the hurricane slash typhoon slash cyclone to move in opposite directions in the southern hemisphere to the northern hemisphere. So if we take a look at the movement of this hurricane, we can see it's counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. But again, anytime that you see things different in the northern hemisphere versus the southern hemisphere, immediately think Coriolis force. Now, when these hurricanes are constantly blowing over the same direction, what's going to happen is it's going to cause water on this leading edge to start to build up. We call this storm surge. Now, this is associated with high winds moving in the same direction. This is going to be associated with flooding, and this is going to be the big damage when we start looking at unfortunately, due to fatalities. Now, there was a superstorm Sandy, which was a hurricane. It wasn't a, it was a hurricane and a nor'easter kind of built together. We tracked the hurricane off the coast, and unfortunately, it hit at high tide. Now, we recall that tides are a function of gravitational pull of the moon and the sun. So if we have a high tide, this is storm surges on top of the high tide. So if you have high tide and a storm surge, this created super high amounts of water. It's just kind of a worst case scenario to create that storm that flooded out subways in New York City not too many years back. So that storm surge, again, is built on, we have average tide height here, pressure surge and from the wind. And so this creates all sorts of problems associated with this bulge of water. And this is what caused, the storm surge caused water to flow in from the Gulf of Mexico up into Lake Pontchartrain with Hurricane Katrina. After the water filled Lake Pontchartrain, as the water was rushing back, it broke some levees and flooded out portions of New Orleans. So the large wall of water that piles up in front of a hurricane is called the storm surge. And so when we start looking at the hurricane, if this hurricane comes in at an angle let me get my drawer out here, my draw function. So the storm surge would be building right along this portion of the storm. And so if depending on how the angle is as a strong storm is approaching, it's approaching right here. Let me erase. But if the storm had a different path, storm was moving in this direction, the storm surge would be up here. So again, it depends on how the storm, or the angle at which the storm is approaching, as well as if we have a city right at that storm surge, that can be really bad. And so if I were looking at this hurricane and tracking this hurricane, we start off with a tropical storm and then it builds to a hurricane. And this is where it was at different points. That's where those H's are. The storm surge would be right along that leading edge. So when we start looking at this, this line is, we'll run this model multiple times with slightly different variables, which we don't have all the data for. And so when we start looking at these hurricanes, we will have the uncertainty path in this case being right in this location. And obviously the further out you are, the more uncertainty you're going to have. So if you have any questions about this chapter, be sure to let me know. Thanks.